So now that we have introduced the nomenclature, I can probably tell you how the motors in these two robots work. The epoch is very small, and you are interested in knowing exactly where the wheels are at every time. And you cannot afford an expensive mechanism that involves an encoder. So people usually choose stepper motors for small robots like this. And this is also the case of the epoch. The controller that is on the microcontroller of the epoch will generate the appropriate pattern for driving the stepper motors at a desired speed, and at the same time keep track of where the stepper motor is, allowing you to control the position of the wheel. In this Bioloid example, the servos made by Webots, which is a Korean company, and called I.2, they use DC motors inside, and they don't use an encoder, but simply a potentiometer, which measures the resistance and allows the controller that is inside the servo motor to determine its position. The I.2 motors also have a digital microcontroller, which allows to set the position and the speed, and sometimes to even control the torque of the motors by regulating the current, which is making it a very sophisticated system. In Webots, motors are abstracted by a device which can be either operated in position control, that is, you set a certain position that you want the robot motor to turn, or velocity, which is given in radians per second. We can best explore this by actually playing with the robot controller, which we will introduce now. In order to create a robot controller, we say file new robot controller, and we will choose, let's call this one basic epoch controller. Alright, we like those directories, and we are done. Now you see the basic script here to the right. The way a Webots controller works, you have to import the robot object from controller and can then create an instance of the robot class, which we do here in 9.8 by saying robot equals robot class parenthesis. The next step in the code is we want to obtain the basic time step that the simulation is running at. This is something that you can see here in the scene tree in the world info. And in this case, the basic time step is 32 milliseconds. Now, the way the robot controller works is in a while loop, and we call the function robot.step with the time step as parameter. So in this case, whenever you call robot.step, you will simulate 32 milliseconds of simulated time. In between, you can read the sensors of the robot and set the actuators, and then call robot.step again, which will actually Now the standard controller already comes with everything we need to turn the motors on, which is here in line 15. The way everything in Webots works is devices have names, and you can use the getDevice function from the motor class to get the device name and a device handle. And in this case, we should look up what the motor names are. And in order to do this, we go and check the epoch robot and go into their children. Now the hinge joints are where we have the motors, and so we see the left wheel motor is called left wheel motor, and the right wheel motor is called right wheel motor. Alright, so in order to do this, we plug these names in here. Left wheel motor, and we call this motor left, and we do the same thing for the right motor. right wheel motor. And now we have the opportunity to set the position of the motors to, let's say, 10, and we do the same with the right motor. Now let's save this, and now let's set the controller in the epoch scene tree. And when you scroll down in the robot, you will see that there's a controller field which currently says generic. Now we can press select, and the basic epoch controller shows up here because we have created this controller in the controller subdirectory of the current project. Now once we return this simulation, maybe we want to press play and see what happens. What do we expect? We expect the robot to drive forward by a couple of rotations. To be exact, 10 is around 3 pi, so we expect this wheel to make 1.5 rotations forward. Let's press play and let's see what happens. Ooh. Alright, so what happened here? Let's rewind a little bit and see what happens. Okay, so either the robot hit the wall or it goes on forever. Let's see what happens when we put it a little further away. Alright, so you see here's the expected behavior. The robot turned for a couple of turns and then stopped. Let's do this again and look more closely at the wheels to see what actually happens. And now what you can do, instead of pressing play, you can press a single step, which advances the simulation by only 32 milliseconds. So what you've seen is an artifact of the physics engine, but you now see the wheel turning forward. And so we are about 1 rotation through, actually 1.5, and that device stops. It has been a little hard to see because of the light source, so let's move this over here. We are not disturbed by the light. Let's rotate the robot a little bit, look at it from the other side, and hopefully now we can better see how often the wheel has turned. All right. So this is half a rotation, 1 rotation, and 1.5 rotations. Now you might wonder, why is he showing us all of this? Why is he not just editing the video and shows out the result at the end? Well, robotics is very experimental or experiential, and when you have a real robot, you would place this on the table, you would let it run, you would realize, oh, I didn't see what went on. You will design a better experiment, you will move it around, you will run it again and again, and Webots actually allows to do that, much like when you would work with a real robot. But now, did you notice something? It's very inconvenient to set or drive the robot around by setting the position of the wheels. This makes a lot of sense when you have a robotic arm or robotic leg, like in this Bioloid example, where you would set absolute positions in order to move the leg or the arms in a certain pose, and then probably even implement a gait that makes the robot walk. Now, when you drive a car, you are very unlikely to drive it by setting the position of each wheel continuously. Instead, what you would want to do is you want to set the speed. Now, as I told you earlier, there are different kinds of motors. The most basic motors can just be controlled in terms of speed. As soon as you add an encoder or use a stepper motor, as in the epoch, you can determine the position. In Webots, you can also choose to set the robot in velocity control mode. And in order to do this, you set the position that you want to be at to infinity. In Python, there is actually a floating point constant which you can reach via the keyword inf, and we do this here, and this is how to set the position to infinity in Webots. Now that the position is set to infinity, you can actually set the velocity of the motors, and the built-in servo that Webots simulates will not fight the position. Now what will happen now, the robot will just turn forward forever, which is not very interesting, so why don't we let it drive in a curve? To have the robot drive in a curve, we have to set different velocities, and what we can do, for example, we can set the left motor to 0, which will make the robot spin around the left wheel's center point in a circle. Let's see if it actually does this. We rewind the simulation. Let's move it a little out of the way of this other robot here and press play. And as we promised, the robot goes in a circle, pivoting around the left wheel. Now we can try something else. We can set the speed here to negative -10 and try this again. Press rewind and see what happens, and as we expect, the robot is spinning in place. Now we can have the robot drive in a larger curve by setting the left wheel to be half the speed of the right wheel, and let's see what happens. When we press play, the robot drives in a large curve.